How can we know what a star hundreds of light years away is made of, or how far it really is? Twilight Observatory Dome opens, revealing a large modern telescope inside. A space telescope, Hubble-like, floats above Earth, its solar panels gleaming against the stars. A dramatic wide view reveals many galaxies scattered across the cosmic void. So how do we measure the vast distances in space? For nearby stars, we use a clever technique called parallax. This method uses Earth's orbit as a giant baseline. As our planet journeys around the Sun, a nearby star appears to shift its position against the backdrop of distant stars. By observing this tiny shift from opposite sides of our orbit, astronomers use simple trigonometry to calculate the star's distance. But for stars too far for parallax, we need standard candles, objects with a known intrinsic brightness. A prime example is the Cepheid variable star. These stars pulsate, and the speed of their pulsation is directly linked to their true luminosity. By comparing this known absolute brightness to how bright they appear from Earth, we can accurately calculate their distance. To peer even deeper into the cosmos, we need brighter beacons. Enter Type Ia supernovae. These powerful stellar explosions have a remarkably consistent peak brightness, making them excellent standard candles. A single supernova can briefly outshine its entire host galaxy, allowing us to measure distances to galaxies billions of light years away. Finally, for the grandest cosmic scales, we use the universe's expansion. As distant galaxies race away from us, their light gets stretched to longer, redder wavelengths, a phenomenon called redshift. Edwin Hubble discovered a profound relationship. The more redshifted a galaxy is, the faster it's moving away, and therefore, the farther away it is. This principle, Hubble's law, is our ultimate tool for mapping the cosmos. So, how do we figure out what stars are made of? For that, we use a powerful technique called spectroscopy, which decodes the messages hidden within starlight. When starlight is passed through an instrument called a spectrograph, it spreads out into a rainbow of colors called a spectrum. But this stellar rainbow isn't perfect. It's crossed by dark absorption lines. These are created when elements in the star's atmosphere absorb specific wavelengths of light. Each element creates a unique pattern of lines, like a cosmic fingerprint. By comparing the star's spectral lines to the known fingerprints of elements tested in a lab, scientists can precisely determine its chemical composition, from hydrogen and helium to heavier elements we call metals. Knowing distance helps us map the universe's grand structure. It allows us to build breathtaking three-dimensional charts of the cosmic web, a vast network of galaxy clusters and enormous empty voids, creating a true celestial atlas. Understanding composition helps us trace stellar life cycles and predict their dramatic ends. We learn how stars fuse elements, which tells us if they will fade away or explode in a spectacular supernova. This knowledge reveals our cosmic origin. It shows how elements like the carbon in our DNA and the oxygen we breathe were forged in the hearts of ancient stars and scattered across space. We are literally stardust. Every time we look at the stars, we are not just seeing light, we're reading the history of the universe. Fade to black, leading into the Physics AI logo reveal in elegant typography.